Europa looks peaceful from a distance. From Earth, or from anywhere in the inner solar system, it appears as a small, smooth, brilliantly white sphere laced with brownish lines, like a porcelain egg with hairline cracks. Among all the moons in the solar system, it is one of the brightest. Its surface reflects roughly 67% of the sunlight that falls on it. It looks clean, cold, still. This is deceptive. Beneath that white surface, beneath an ice shell estimated anywhere from a few to several tens of kilometers thick, there is an ocean. Liquid water. Salty, possibly warm near the bottom, maintained by tidal heating from Jupiter's gravity, possibly containing chemical gradients at a rocky seafloor. This makes Europa, in the view of many planetary scientists, the most promising place in our solar system to search for extraterrestrial life. But tonight, we are not asking about the search for life on Europa. We are asking a different question, one that is raised far less frequently and which, examined carefully, turns out to be far more complex. What if we tried not just to visit Europa, not just to send a probe there, but to actually establish a base? What if we tried to live on Europa, or at least work there long enough to make it meaningful? As soon as you ask that question concretely, you begin to understand how fundamentally Europa differs from Mars in terms of the conditions for human survival. Mars is harsh. This is well known. Atmospheric pressure at about 0.6% of Earth's, mean temperature around -60 degrees Celsius, an atmosphere composed primarily of carbon dioxide, providing essentially no protection from radiation, toxic dust storms that can last months. All of this is real and serious. But Mars is at least on a surface. Mars is at least within reach of sunlight. Mars does not orbit within the radiation belts of one of the most powerful planets in the solar system. Europa is different. Tonight we will follow this honestly, without simplification, without minimizing. We will examine each of the factors that makes living on Europa not merely more difficult than Mars, but qualitatively, fundamentally, more dangerous. Not because Europa is not worth studying, but precisely because it is so worth studying, and because understanding the real conditions there is necessary for any honest conversation about its future as a destination. If the night is long, stay. Europa is one of the most remarkable and least understood objects in the solar system, and it is far more dangerous than it looks. Let us begin with the most obvious and most fundamental issue: radiation. Jupiter is the largest planet in the solar system, 318 times the mass of Earth. Its enormous mass and rapid rotation, one full turn in roughly 10 hours, generate the most powerful magnetic field of any planet in the solar system. Jupiter's magnetic field is approximately 20,000 times stronger than Earth's. This enormous magnetic field captures charged particles, electrons, protons, sulfur and oxygen ions, predominantly ejected by the volcanoes of Io, and accelerates them to high energies, trapping them in radiation belts around the planet. Jupiter's radiation belts are the analogue of Earth's Van Allen belts, but incomparably more intense. Europa orbits directly inside these radiation belts. The surface of Europa receives a radiation dose of approximately 540 sieverts per day. 1 sievert is a dose at which roughly 5% of people develop cancer. 4 sieverts is a lethal dose for half of untreated people. 8 sieverts is essentially lethal without treatment. 540 sieverts per day. This means an unprotected person on the surface of Europa would receive a lethal radiation dose in approximately 20 minutes, less than half an hour. the amount of time a person spends on an ordinary lunch break. This is not simply high radiation, as on Mars or in orbit on the ISS. This is a qualitatively different scale. For comparison, the surface of Mars receives roughly 0.2 sieverts per year, already significantly exceeding Earth's safety standards, but incomparable to what happens on Europa. Mars's surface receives roughly 1,000 times less radiation in a year than Europa's surface receives in a single day. The difference is not one of degree, it is an order of magnitude difference. One might object that shielding solves this problem, that a sufficiently thick barrier of lead, polyethylene, water, or other materials can protect a habitat. This is true in principle. Good enough shielding can reduce radiation doses to acceptable levels. But good enough in Europa's conditions means several meters of water or several meters of appropriate protective material. That is enormous mass, enormous volume. And it means that delivering such shielding to Europa already raises the question of mission cost and complexity to a level completely beyond anything contemplated for a Mars base. Let us talk now about distance, because the distance from Earth to Europa makes it a fundamentally different destination than Mars in terms of survival logistics. Mars, at its closest approach to Earth, is about 54.6 million kilometers. At its farthest, about 401 million kilometers. Travel time for uncrewed spacecraft under favorable conditions, roughly 6 to 9 months. For crewed missions with optimal trajectories, comparable. Jupiter, at its closest point to Earth, about 588 million kilometers. At its farthest, more than 900 million kilometers. Travel time for uncrewed spacecraft from 2 to 6 years, depending on trajectory. Galileo took 6 years. Voyager reached Jupiter in roughly 2 years using gravity assists. Juno took about 5 years. For a crewed mission to Europa, with current chemical rocket propulsion, transit time would be a minimum of several years, most likely 3 to 6 years one way. This is incomparable to what a Mars mission requires. This means that in the event of any crisis at a Europa base, medical, technical, life-threatening, assistance from Earth is unreachable within any feasible time frame. On Mars, we are talking about 6 to 9 months waiting for help in the worst case, which is already extreme. On Europa, we are talking about years, but communication delay compounds this further. On Mars, the signal delay is 3 to 22 minutes one way. On Europa, roughly 32 to 52 minutes one way, depending on orbital configuration. A reply to a simple question takes more than an hour. Instructions in an emergency arrive more than an hour after the situation has already developed. This means a Europa base crew must be capable of making all critical decisions autonomously, without any possibility of consulting Earth in real time, in conditions where any error is potentially irreversible. Let us talk now about the third fundamental problem, Europa's surface itself, which is active and unstable in ways that make it unlike any other destination under consideration. Europa's surface is not solid ice in the way we typically think of ice. It is a geologically active, living surface, constantly subject to processes that make construction on it extraordinarily difficult. Jupiter's tidal forces, the same ones that heat Europa's interior and sustain its liquid ocean, create significant mechanical stress on the surface. The surface ice of Europa experiences tidal deformation as Europa moves through its elliptical orbit. The changing gravitational pull of Jupiter, Io, and Ganymede continuously stretches and compresses the icy shell. The lineae, those brownish lines that give Europa its characteristic appearance, are cracks and ridges formed by these tidal stresses. Some are geologically fresh, formed within the last few million years. It is not impossible that some are forming right now. What does this mean for building a base? Any structure placed on Europa's surface must withstand the ongoing tidal stress of the icy shell. Cracks can open beneath a structure. Ice can move. Structures that appear stable today may be at the edge of a new fracture in 100 years. This is not a hypothetical threat. It is a direct consequence of Europa's observed geological activity. The geologically dead surface of Mars, for all its harshness, is at least predictable. Europa is geologically alive. Beyond tidal deformation, there is another type of surface activity characteristic of Europa: chaotic terrain. These are extensive regions where the icy shell appears to have been disrupted from below, possibly due to temporary thinning or breakthrough from the subsurface ocean, and reorganized into randomly oriented hummocky terrain. These regions are geologically unstable and poorly suited for construction. Let us talk now about Europa's gravity and what its inadequacy means for long-term human habitation. Gravity on Europa's surface is approximately 0.134 g, about 13.4% of Earth's gravity. This is significantly less than on Mars, where gravity is about 0.38 g, 38% of Earth's. We already know from ISS experience and long-term spaceflight that life in reduced gravity or microgravity has significant negative effects on the human body. Bone density loss, about 1 to 2% per month in the spine and hips in zero gravity. Muscle atrophy, redistribution of body fluids with increased intracranial pressure. Vision problems associated with this pressure. Cardiovascular changes. On Mars, with its 0.38 g, these effects are expected to be less severe than in microgravity, though we have no long-term data on life at 0.38 g. But even that value is significantly closer to 1 g than Europa's 0.134 g. On Europa, we are talking about gravity roughly 3 times less than Mars, and about 7.5 times less than Earth. This gravity is insufficient to maintain normal functioning of the human skeleton, muscular system, cardiovascular system, and neurovestibular system under long-term exposure. Assume a crew spends 2 years on Europa. With intensive exercise, which would itself be complicated by the difficult environment, they would still experience significant bone density loss and muscle tissue loss, possibly irreversible at such lengths of exposure. This is not an abstract medical detail. It is a concrete constraint that determines how long people can remain on Europa, and it is much more restrictive than on Mars, precisely because of the difference in gravity. Let us talk about Europa's surface temperature and what it means for the base's energy requirements. The mean surface temperature of Europa is about minus 160 degrees Celsius. Near the equator at midday, it can rise to roughly minus 110 degrees. At the poles, it drops to minus 220 degrees Celsius. For comparison, Mars's mean surface temperature is about minus 60 degrees. Martian nights can reach minus 125 degrees. This is cold, but it is not the extreme, stable cold that exists on Europa. The difference in temperatures has direct engineering consequences. At minus 160 degrees, ordinary lubricants solidify. Metals become brittle. Sealing gaskets lose elasticity. Electronic components require special design for operation at these temperatures. Spacesuits for working at minus 160 under intense radiation bombardment are fundamentally more complex than Mars suits. Maintaining temperature inside a habitat at external conditions of minus 160 requires continuous heating. Thermal losses through the module walls at this temperature differential will be significant, even with good insulation. This means a constant energy expenditure simply to maintain a survivable temperature. Where does this energy come from? On Mars, 2 primary candidates: solar panels and nuclear reactors. Solar panels on Mars work less efficiently than on Earth because of the greater distance from the Sun. Mars receives about 43% of Earth's solar flux. But they work. On Europa, the solar flux is about 3.7% of Earth's, 50 times less than Earth and roughly 12 times less than Mars. Solar panels on Europa would be extraordinarily inefficient. They would need an enormous area to produce any meaningful amount of power. And this while operating under intense radiation bombardment that degrades solar panels over time, reducing their efficiency as radiation damage accumulates in the materials. Nuclear reactors are the only realistic energy source for a Europa base. This is achievable. Small nuclear reactors, such as those being developed under the Kilopower program, can produce from 1 to 10 kilowatts of electrical power. Larger systems, more. But they are heavy. They must be delivered to Europa, already a colossal logistical challenge, and then deployed and commissioned on the surface. And here a certain irony is worth noting. A nuclear reactor on Europa's surface adds yet another source of radiation to an already extreme radiation environment. Shielding the reactor from the habitat, another engineering challenge on an already long list. Let us now talk about the seventh problem, Europa's surface chemistry, which presents its own independent risk and is rarely thought about when discussing a potential Europa base. Europa's surface is not composed of pure water ice. Radiation processing of surface ice and delivery of sulfur and other ions from Jupiter over billions of years has created a rich chemistry. Spectroscopic observations have detected sulfates, chlorides, sulfur dioxide, and possibly sulfuric acid on Europa's surface. Particularly concerning are the sulfates and acids. If material from the subsurface ocean reaches the surface through cracks, and geological data suggest this happens, it carries salts and other substances from the ocean. Under intense radiation, these are converted to chemically aggressive compounds. This means the dust on Europa's surface, which will inevitably be present and will inevitably accumulate on equipment surfaces, spacesuits, airlocks, is chemically aggressive. Not just mechanically abrasive like lunar or Martian dust, chemically reactive. Prolonged contact with this dust potentially damages spacesuit materials, hatch seals, instrument optics. Inhalation of particles of this dust is biologically hazardous. On Mars, dust contains perchlorates, toxic compounds presenting a biological threat. But perchlorate Martian dust is not chemically aggressive in the sense of corroding metals and polymers. Europa's dust creates threats simultaneously biological and engineering in character. Let us now talk about the subsurface ocean pressure and what it means for the structural integrity of any surface installations. Europa's ice shell is in continuous mechanical interaction with the liquid ocean below. Tidal heating creates convective movements in the ocean. This convection creates pressure on the underside of the ice shell that over time can lead to vertical ice movement, uplifts and subsidences of the surface. This effect, sometimes called Europa's breathing, has been instrumentally observed. Galileo data and subsequent studies suggest Europa's surface experiences tidal deformation with amplitude possibly reaching several meters over one orbital period, 3.5 Earth days. Several meters of vertical surface displacement in 3.5 days. This is not a catastrophic earthquake, but it is slow, continuous, unavoidable surface deformation that has no analogue on Mars or the Moon. Any structure anchored to Europa's surface must either accommodate these deformations, meaning flexible joints, shock absorbers, compensating elements, or be sufficiently decoupled from the surface to not transmit deformations to the structure. Both approaches add complexity and reduce reliability. And if the ice shell is thin enough in some regions, estimates of shell thickness range from a few kilometers in the thinnest places to several tens of kilometers, There is a theoretical possibility that bottom pressure periodically creates local instability zones where ice can partially melt, move, subside. Choosing a base location accounting for long-term stability of the ice shell is an extremely difficult challenge we cannot solve at our current level of knowledge about Europa. We lack data on shell thickness at specific points on the surface with sufficient resolution to select a safe construction site. Let us now talk about the ninth problem, the biological risk in both directions. If there is life in Europa's ocean, and this remains a hypothetical possibility, not a confirmed observation, then any contact between the base and that ocean creates a bidirectional biological risk. Risk 1. Contamination with Earth life. Any Earth microorganisms that reach Europa's ocean, through a leak, through a crack in the ice shell beneath the base, through waste, could potentially compete with or destroy local life. This is an ecological catastrophe that cannot be undone. Risk 2. Back contamination. If European microorganisms, if they exist, enter the base life support system, they will encounter human immune systems that have no evolutionarily accumulated defense against any extraterrestrial biology. The consequences are unpredictable. They could range from neutral, if extraterrestrial microorganisms are simply incompatible with Earth biology, to catastrophic if they prove pathogenic in ways we cannot foresee. This is not science fiction. This is the principle of planetary protection taken seriously in NASA and COSPAR documents. Europa is classified as a Category 3 to 4 object on the planetary protection scale, the highest category of caution, precisely because it is a potentially habitable environment, and any missions to it must comply with the strictest biological isolation requirements. Creating a permanent crewed base on Europa, with people who are by definition not sterile, creates a fundamental contradiction with planetary protection principles. Humans carry trillions of microorganisms. Complete biological isolation of a crewed base from the surrounding environment is practically impossible on long timescales. This means creating a base on Europa requires not just engineering solutions, it requires making a fundamental ethical decision about whether we are willing to risk contaminating a potentially living world ocean for the sake of scientific and exploratory purposes. Mars creates a similar problem, to a lesser degree, since liquid water on Mars's surface is absent, and potentially habitable regions, if they exist, are considerably deeper and less accessible. But Europa, with its ocean immediately below the ice shell, raises this question far more sharply. Let us now talk about the specific scientific reason why, despite all these dangers, Europa remains a priority scientific destination, and why robotic missions rather than crewed missions are the realistic near-term strategy. The Europa Clipper mission, a NASA spacecraft launched in October 2024, is the most ambitious ever sent to Europa. Unlike Galileo, which explored the entire Jupiter system with rare flybys past Europa, Clipper will perform roughly 50 close flybys of Europa over 4 years of operation. Clipper does not enter orbit around Europa, precisely because of radiation. A permanent orbit around Europa would mean constant residence in the most intense radiation fields. The spacecraft's electronics would be destroyed too quickly. Instead, Clipper orbits Jupiter and periodically passes Europa at minimum distance, diving into the intense radiation belts briefly with each flyby. This is technically brilliant, but it also vividly demonstrates the reality of the radiation problem. We cannot allow even an uncrewed spacecraft to remain in permanent orbit around Europa because of radiation, to say nothing of people. Clipper will map Europa's surface at high resolution, measure ice thickness with radar, analyze surface chemistry and any material plumes ejected into space from possible active regions, measure the magnetic field and gravitational field to map internal structure. The scientific return from Clipper will be enormous, but Clipper's data alone will not resolve the fundamental question about life in Europa's ocean. For that, we will need either a spacecraft capable of drilling through the ice and entering the ocean, a technological challenge of decades, or analysis of material from possible water plumes that may carry material from the ocean to the surface. Let us now talk about what realistic next steps look like after Clipper, about the timeline that leads eventually, perhaps, toward human presence. The next logical step after orbital reconnaissance is a lander, a small surface vehicle capable of drilling a few centimeters or meters into the ice and analyzing its composition directly on site. NASA has studied conceptual designs for such a vehicle, Europa Lander, but it is not yet funded as a full mission. The primary problem for a lander is radiation. Even an uncrewed vehicle on Europa's surface will be exposed to the same 540 sieverts per day. Its electronics must be radiation hardened enough to operate for at least several days or weeks. This is technically achievable with appropriate shielding and radiation hardened components, but adds to the already formidable challenge of landing on Europa. After a lander, the next step is a penetrator or drilling vehicle capable of passing through the ice shell to liquid water. This is a technological challenge of an entirely different scale. Drilling through potentially tens of kilometers of ice at minus 160 degrees requires a thermal drill, a vehicle that melts ice ahead of it and slowly descends, leaving a refreezing channel behind. Theoretically achievable, practically never done even on Earth in anything approaching Europa-like conditions. And after penetrating the ocean, the planetary protection question arises in its sharpest form. Can we send a vehicle into Europa's ocean without contaminating it with Earth microorganisms? This is not a technical question. It is an ethical and scientific question requiring international consensus and decisions not yet made. But it is toward the answer to this question that all these steps lead. Is there anyone in that ocean? We do not know. We intend to find out. And human presence on Europa, if it ever becomes possible, will be the final link in this chain. Not the first, not the second, perhaps not the 10th, but the direction is set. Because the question at the end of this path is one of the most important questions humanity has ever asked. Are we alone in the universe? Or in the dark ocean beneath kilometers of ice in the Jupiter system? Right now, while you read these words, is something swimming, growing, living? We do not know the answer, but we know where to look. Let us talk about what a spacesuit for working on Europa's surface would actually need to accomplish, because the comparison with a Mars suit makes the qualitative difference in difficulty immediately concrete. A Mars spacesuit is already an engineering achievement of the highest order. It must maintain pressure of roughly 55 kilopascals, approximately half the pressure of the summit of Everest, inside a flexible shell that permits movement. It must protect against temperatures from plus 20 to minus 125 degrees Celsius. It must provide oxygen supply, carbon dioxide removal, pressure maintenance, thermal regulation. It must have basic protection against ultraviolet radiation and against the modest radiation background of the Martian surface. It must weigh no more than effective work at Mars's 0.38 g allows. All of these challenges are solvable. NASA has active Mars suit development programs, and conceptual designs exist in an advanced state. A Europa suit must do everything a Mars suit does, and additionally, first, protect against temperatures of approximately minus 160 degrees Celsius rather than minus 125. That is 35 degrees of additional thermal challenge, requiring more powerful heating systems, better insulation, more cold-resistant materials for the moving joint mechanisms. At -160, ordinary polymers become brittle. Standard lubricants stop working. Sealing gaskets lose elasticity. Every suit joint, every mechanism allowing movement of fingers, wrists, elbows, knees, must function reliably at this temperature. Second, provide radiation protection at a level permitting surface presence for at least several hours. At a background dose of 540 sieverts per day, 22.5 sieverts per hour, even 2 hours outside without protection means a dose of 45 sieverts, far beyond lethal. To reduce the received dose to a level permitting a few hours of surface work, say 1 sievert for a 2-hour excursion, which is already an exceptionally high single dose, the suit must provide flux suppression of a factor of roughly 45. This requires several centimeters of hydrogen-containing material integrated into the suit. Several centimeters of additional shielding distributed across the entire suit means significant additional mass. At Europa's 0.134 g gravity, this is somewhat less critical than at Earth gravity, but Europa's gravity does not allow unlimited mass growth. The suit must remain mobile, workable, not so heavy as to paralyze movement. Third, be chemically resistant to the aggressive environment of Europa's surface dust. The suit's outer materials must withstand contact with sulfates and other acidic compounds without degradation. This constrains polymer selection and raises questions about material service life under repeated excursions. Fourth, operate reliably under continuous radiation bombardment that degrades the electronics of the life support system. Sensors, controllers, displays, communication systems, all electronic components slowly destroyed under radiation exposure. A suit that performs perfectly on the first excursion may accumulate damage with each subsequent one. Fifth, account for Jupiter itself. This is a less obvious point, but worth attention. Jupiter from Europa's surface appears as an enormous object, angular diameter of about 24 degrees, roughly 48 times the apparent diameter of the Moon seen from Earth. It is a significant source of thermal infrared radiation. The suit's thermal engineers must account for heat exchange with this enormous warm object in the field of view rather than simply with cold space. All of this makes a Europa suit not simply an improved Mars suit, but a qualitatively different object. An engineering article representing an entirely new level of complexity. Can such a suit be built? Probably, yes, with sufficient funding and time. But the development, testing and certification of such a device would take decades and cost sums comparable to the development of entire launch vehicles. Let us now talk about the specific engineering concept considered most realistic for long-term presence on Europa, a base embedded in the ice with minimal external elements. The concept of an under-ice base rests on the following logic. If the primary killer on Europa is radiation, and ice is an effective radiation shield, then placing living quarters under several meters of ice solves the main problem passively, without needing to deliver heavy shielding from Earth. How this could work? First phase, without people. Robotic vehicles deploy thermal drills that melt the ice and create cavities at a depth of several meters. Inflatable or folding habitat modules are lowered into these cavities, wrapped in a thin layer of additional shielding. The cavities fill with water around the module, which refreezes, fixing the module in place and providing additional shielding. On the surface remains only what is necessary: communication antennas, the nuclear reactor's power conduit outlet, airlocks for suited excursions. All of this minimal, maximally protected. The nuclear reactor is placed at some distance from the habitats and provides electrical power through wired connections. The reactor's heat also helps maintain temperature in the habitat module. The habitat cavities are lit by artificial light. No access to sunlight, not because it is impossible in principle via fibre optics, but because the amount of sunlight reaching Europa is so small that the psychological value would be negligible regardless. Water from melted ice is used for drinking, hygiene, hydroponic food growing, and additional radiation shielding. Water tanks placed along the walls add to the protection provided by the ice outside. This sounds realistic at the conceptual level, but detailed engineering examination reveals problems. First, stability of ice cavities. Ice is not an ideal structural material. Under the pressure of overlying layers and thermal influence from the habitat module, it can slowly deform, flow in the sense that glaciers flow downhill. The habitat cavity may slowly close over time. Structural measures are required: cavity reinforcement, maintaining ice temperature below critical values for creep. Second, water pumping systems. When ice melts around the drills, the resulting water must be efficiently pumped out before it refreezes. Pumping systems for operation at -160, yet another specialized engineering challenge. Third, airlocks and transition zones. Exiting from the subterranean habitat module to the surface requires an airlock withstanding the temperature differential from comfortable interior conditions to -160 outside. This airlock is potentially a weak point in the protective barrier. Every surface excursion means opening this barrier and partial disruption of radiation protection. Fourth, geological instability. Europa's ice shell experiences tidal deformations. A subterranean module embedded in ice will experience these deformations together with the surrounding ice. The module structure must withstand cyclic mechanical loads from tidal compression and extension of the shell. All of this is solvable, in principle. None of these problems is fundamentally unsolvable with sufficient engineering effort and funding, but the totality of requirements makes building such a base a project that in complexity and cost exceeds by orders of magnitude anything previously conceived in crewed spaceflight. Let us now talk about what the comparison between Mars and Europa tells us about the fundamental principles of selecting destinations for human spaceflight. Mars, for all its harshness, is a place where human presence makes engineering sense. It is within reach of current technologies. Its surface is accessible in spacesuits. Its resources are partially available for local use. Its radiation environment is harsh but manageable. Its gravity, a third of Earth's, is insufficient but significantly better than the Moon's or Europa's. Europa, for all its scientific interest, is a place where human presence faces qualitative rather than merely quantitative difficulties. Not simply harder than Mars, but a fundamentally different category of difficulty. Radiation that kills in 20 minutes, distance measured in years rather than months, temperature destroying ordinary materials, surface that cracks and moves under Jupiter's tidal pressure, chemically aggressive surface environment, virtually no solar energy, biological contamination risk in both directions. This does not mean people will never be on Europa. Technological capabilities continue advancing. Fusion propulsion as an energy source for interplanetary ships could radically reduce transit times. New radiation shielding materials, medical technologies for mitigating radiation exposure effects, artificial gravity systems. But in any reasonable time horizon, across the next several decades, Europa remains a fundamentally more difficult destination for human presence than any other considered location in the solar system. Significantly more difficult than Mars, significantly more difficult than the Moon, possibly more difficult than Mercury or Venus's surface, if only the radiation component of risk is assessed. And yet Europa draws us, because beneath that ice that kills in 20 minutes, beneath that chemically aggressive surface in Jupiter's tidal belts, there is more liquid water than on all of Earth's surface combined. An ocean that has existed probably for billions of years. An ocean with heat sources at its bottom. An ocean with all the components we associate with the potential origin of life. Europa is dangerous precisely because it is interesting. The physical conditions that make it such a harsh place for people, tidal heating from Jupiter's gravity, intense radiation, chemically active surface, are the product of the same system that sustains the liquid ocean within. Jupiter simultaneously nurtures Europa and makes its surface practically uninhabitable for humans through the same magnetic fields that are a consequence of its size. This is one of the most beautiful and most merciless examples of the interconnectedness of conditions in the solar system. What makes Europa possibly alive kills us. What could support life there makes it unreachable for us physically. Let us now talk about one final aspect that is rarely discussed in popular treatments of Europa, about what it would actually feel like to be there in the most immediate physical sense. Imagine standing on Europa's surface in a spacesuit. You have exited the airlock. Your suit's radiation dosimeter is ticking. You know you have perhaps 2 hours before your accumulated dose reaches the limit for a single excursion. Above you, covering an enormous fraction of the sky, hangs Jupiter, not as a point of light, as a disk 24 degrees across, banded with clouds, its colours visible to the naked eye. The great red spot possibly visible near the limb, Io somewhere nearby, a warm orange dot emitting its sulphurous plumes. The other Galilean moons distributed across the sky. The surface around you is white and brown streaked, intensely cold, lit by sunlight roughly equivalent to a slightly overcast day on Earth. Dim but not dark, casting sharp shadows in the near vacuum. The horizon is close. Europa is small, its horizon curves sharply. Everything around you wants to kill you. The ice beneath you is geologically active. The radiation environment above you is lethal without your suit. The surface dust coating your suit's exterior is chemically aggressive. The temperature would instantly destroy exposed biological tissue. And the ocean you have come to study, the entire reason for being here, is kilometers beneath your feet, separated from you by ice you cannot penetrate with your gloved hands. No human being has ever experienced anything like this. The nearest analogues, deep-sea diving, Antarctic fieldwork, high-altitude mountaineering, spacewalks from the ISS, each capture one or two aspects of the extreme environment. None captures the totality. The specific character of the danger on Europa is not that any single factor is uniquely unprecedented. Each individual factor, cold, radiation, distance from Earth, surface instability, exists in some form in other extreme environments humans have encountered. It is the combination, the simultaneity of all of them. The fact that there is no retreat, no warm room a few hundred meters away, no rescue helicopter, no decompression chamber, nothing but the suit and the base and the vast empty distance back to Earth. This is what living on Europa would mean in the most concrete human terms. Not the statistics of radiation doses and orbital mechanics and engineering specifications. A person standing on the ice, counting minutes, watching Jupiter overhead, knowing that beneath their feet may be the only other ocean in the solar system that might be inhabited. That is Europa, and that is why, despite everything, despite the radiation, the distance,
the cold, the instability, the biological risk, the energy problem, the impossible logistics. The question of Europa will not leave us alone, because the question it poses is too important to abandon. And the answer, whatever it is, will change everything. Let us talk about something that connects all the dangers we have discussed to a broader question, about what Europa represents in the history of humanity's understanding of where life can exist. Before the 1970s, the consensus view in astrobiology, to the extent the field existed at all, was that life required sunlight. The logic was straightforward. Every ecosystem we knew on Earth ultimately traced its energy back to photosynthesis. Plants captured solar energy. Animals ate plants, or ate animals that ate plants. The food web pointed upward, toward the sun. This consensus was shattered in 1977 when oceanographers aboard the research vessel Alvin descended to the Galapagos Rift, a section of the mid-ocean ridge system in the Pacific, and found something that should not have existed according to prevailing assumptions: hydrothermal vents. Cracks in the seafloor through which superheated, mineral-rich water erupted from the planet's interior. And around those vents, in complete darkness, under crushing pressure, far beyond any possibility of sunlight, a flourishing ecosystem. Tube worms nearly 2 meters long, mussels, crabs, shrimp, fish, an entire food web supported not by photosynthesis but by chemosynthesis, microorganisms using the chemical energy of hydrogen sulfide reacting with oxygen to fix carbon, producing organic molecules that the entire ecosystem fed upon. This discovery did not just add a new data point to ecology, it fundamentally changed the concept of habitable environment. Life did not require sunlight. Life required energy in some form, liquid water, and the chemical building blocks of organic chemistry. If those three things were present, life apparently found a way. The implications for Europa were immediate and obvious, even in 1977, though Europa's subsurface ocean was not confirmed until the Galileo mission in the 1990s. A world with a liquid ocean sustained by internal heat, with a rocky seafloor where hydrothermal activity was possible, with the chemical ingredients delivered by billions of years of comet and asteroid bombardment. This was a potential analogue of the hydrothermal vent environment discovered in 1977. Not a certain analogue, a potential one. But the possibility was real in a way it had not been before the Galapagos discovery. In the decades since 1977, we have found hydrothermal vent ecosystems in every ocean on Earth. We have found life in conditions previously considered incompatible with any biology. In acidic hot springs at pH values below 2, in hypersaline lakes nearly saturated with salt, in ice cores kilometers deep in Antarctic glaciers, in rock cores drilled kilometers into the Earth's crust. In every environment we looked, we found life adapted to it. This pattern, life filling every available niche where the basic physical and chemical prerequisites are met, is what gives the concept of a Europa ocean its scientific weight. Not certainty that life is there, but a pattern of Earth life demonstrating that if the conditions exist, life has a way of being present. The danger that makes Europa so hard to reach for humans is simultaneously the argument for why its ocean might be inhabited. Tidal heating from Jupiter sustains liquid water. Chemical energy from hydrothermal activity at the sea floor sustains potential food webs. Billions of years of stable conditions allow evolution to find whatever niches are available. This is the tension at the heart of Europa. The same system that makes it lethal to visit makes it potentially alive. Let us now talk about what specifically distinguishes Europa from the other ocean worlds in the solar system, from Enceladus, Titan, Ganymede, Callisto.
because understanding Europa's place in this group clarifies why it attracts such specific attention. Enceladus, Saturn's small icy moon, has confirmed liquid water geysers actively erupting from its subsurface ocean right now. The Cassini spacecraft flew through these plumes and directly sampled their composition. It found water, molecular hydrogen, a product of hydrothermal reactions between hot water and rock, organic molecules, silica particles indicating rock-water interactions at high temperatures. This is the most direct observational evidence for active hydrothermal chemistry in any ocean beyond Earth currently known. Why then is Europa considered at least as compelling as Enceladus? Size. Enceladus is about 500 kilometers in diameter. Its ocean, while confirmed, is probably modest in volume. Europa is about 3,100 kilometers in diameter, comparable to Earth's moon. Its ocean volume is estimated to exceed all of Earth's oceans combined. More ocean means more possible environments, more possible niches, more possible complexity in whatever biology might exist. Stability. Enceladus is so small that its tidal heating may be episodic. It may go through cycles of heating and cooling over geological time, potentially freezing and remelting its ocean. Europa's larger size and its specific orbital resonance with Io and Ganymede, which drives the tidal heating, suggests more stable, long-term ocean conditions. 4 billion years of relatively stable liquid water is a far longer runway for evolution than a more intermittent system. Geological diversity.
Europa's surface shows evidence of multiple geological processes: plate-like tectonic activity, chaotic disruption, recent resurfacing, suggesting a dynamic interior with the kind of geological complexity that on Earth is associated with varied hydrothermal environments and chemical diversity. Titan, Saturn's largest moon, is genuinely different in kind from Europa. It has liquid on its surface, lakes and seas of liquid methane and ethane, and a dense nitrogen atmosphere. The possibility of life in Titan's hydrocarbon lakes would be life of a completely different kind from Earth life, using liquid methane as a solvent rather than liquid water. This is fascinating, but far more speculative and chemically alien than water-based life in Europa's ocean. Ganymede has a probable subsurface ocean, but it is sandwiched between layers of high-pressure ice rather than in direct contact with a rocky sea floor. Without rock-water contact, hydrothermal chemistry is severely limited.
Callisto likely has a subsurface ocean, but with minimal tidal heating and lower internal activity, a less dynamic chemical environment. Europa sits at a specific intersection of properties, large enough to have a substantial, stable ocean, close enough to Jupiter to have sufficient tidal heating, with an ocean in direct contact with a rocky seafloor where hydrothermal activity is plausible, with evidence of chemical exchange between the surface and interior, that makes it a uniquely compelling case among ocean worlds. Let us talk about what the James Webb Space Telescope has recently revealed about Europa that has increased scientific excitement about its potential. In 2023, Webb's near-infrared spectrograph observed Europa and detected carbon dioxide on its surface in concentrations and spatial distributions pointing to a specific origin. The key finding was not merely that CO2 was present, it had been detected before, but that its distribution correlates with young geological features on Europa's surface, the disrupted chaos terrain regions where the ice is freshest and most recently resurfaced. This correlation is significant. If CO2 had been delivered from external sources, from meteoritic bombardment, from Jupiter system material, it should be distributed more uniformly across the surface, or concentrated in crater regions. Its concentration in young geological terrain suggests it originates from the subsurface, from the ocean itself, brought to the surface through the geological processes that created those terrains. Carbon dioxide from an internal source means dissolved inorganic carbon in the ocean. Dissolved carbon is a fundamental prerequisite for carbon-based biochemistry.
In Earth's hydrothermal vent ecosystems, the availability of dissolved inorganic carbon is one of the factors determining the productivity of chemosynthetic ecosystems. The Webb CO2 detection does not prove biological activity, but it does confirm that Europa's ocean contains the carbon chemistry necessary for life as we know it, and that this chemistry communicates with the surface in ways potentially accessible to future surface or near-surface measurements. Webb also confirmed previously detected salt signatures, magnesium chlorides, sodium chlorides, whose spatial distribution correlates with young surface features in the same pattern as the CO2. Multiple independent chemical signatures, all pointing to the same conclusion. The ocean is chemically active, its material reaches the surface, and its chemistry contains the ingredients associated with potential habitability. This is the current state of Europa science. We have not detected life. We have detected the chemical prerequisites for life in an ocean that exists around a rocky seafloor where heating occurs after billions of years of stable conditions. The next measurement, whether from Clipper's mass spectrometer sampling possible plumes, or from a future lander analysing surface chemistry, or eventually from a probe that reaches the ocean itself, will move us closer to the fundamental question. Let us now talk about the specific concept of what makes something habitable, and why Europa scores highly on every metric. Because understanding habitability formally makes clear why Europa is taken so seriously, despite the enormous difficulty of reaching it. Astrobiologists use a set of criteria for evaluating potential habitability. While different researchers weight these differently, the core list typically includes liquid water as a solvent, an energy source for metabolism, the chemical building blocks of life, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the CHNOPS elements. Sufficient thermodynamic stability over geological time for complex chemistry to develop. Liquid water. Confirmed on Europa, sustained by tidal heating with a total volume exceeding Earth's oceans. Check. Energy source. Tidal heating maintains the ocean in liquid form and likely drives hydrothermal activity at the seafloor, where chemical energy is available through reactions between reduced hydrothermal fluids and oxidized ocean water. The radiolytic oxidants produced at the ice surface and potentially delivered to the ocean provide an additional energy source. Check. CHNOPS elements. Carbon detected by Webb in the ocean-derived CO2. Hydrogen in the water itself and potentially from hydrothermal reactions. Nitrogen, phosphorus, sulfur. Not directly confirmed in the ocean, but present in the broader Jupiter system material and in meteor and comet inputs, and phosphorus and sulfur detectable in surface materials. Probable check. Thermodynamic stability. Europa's ocean has likely been liquid for billions of years, the same timescale over which complex life evolved on Earth. The tidal heating mechanism is stable as long as the orbital resonance with Io and Ganymede persists, which it will for the foreseeable astronomical future. Check. On every habitability metric, Europa either checks the box or has strong indirect evidence for it. This is what distinguishes it from, say, Mars, where we have evidence of past habitability billions of years ago, but minimal evidence of present habitability, or from the outer giant planets, where conditions are far more extreme and less compatible with biology as we understand it.
Europa's habitability case is about the present, not the past. About ongoing conditions, not ancient remnants. About an environment that potentially hosts life right now. This is why the danger of reaching it is accepted as the price of asking the question. Let us now talk about the timing of the current moment in Europa exploration, about why this specific decade, the 2020s, is pivotal in the history of how we understand this moon. For most of the time since Galileo discovered Europa in 1610, it was simply a point of light moving around Jupiter. For most of the time since Voyager photographed its cracked surface in 1979, it was an interesting geological object. For most of the time since Galileo's magnetic measurements in the late 1990s confirmed the subsurface ocean, Europa was an astrobiological hypothesis, compelling but untestable with available instruments. Europa Clipper, launched in October 2024, represents the transition from hypothesis to investigation. For the first time, we have an instrument capable of characterizing Europa's ocean indirectly, mapping the ice thickness, measuring the magnetic field variations that reveal ocean depth and salinity, detecting and analyzing chemical plumes, if they exist, with the precision and data volume needed to guide the next generation of missions. The data Clipper returns between 2030 and 2034 will determine the strategy for the following decades. If the ice is thin in certain regions, if plumes are confirmed and chemically rich, if the magnetic measurements reveal an ocean with specific salinity and depth parameters, the next mission's design becomes far more constrained and far more specifically targeted. This is the scientific process operating on a human timescale, a career's worth of waiting for each step. Scientists who designed the experiments on Europa Clipper have spent decades on those designs. Many of them will be at or past retirement age when Clipper completes its mission. The next generation of scientists will design the missions Clipper's data makes possible. The generation after that will potentially see the first sample return or first ocean contact. Science at this scale is necessarily multi-generational. This is not a failure of ambition. It is the nature of doing science responsibly at the frontier of what is technically possible. The danger of Europa does not diminish with time in most of its forms. Radiation is a physical constant. Distance is orbital mechanics. The ice is as thick as it is. But our capacity to work within and around those constraints grows with each decade of technological development. The question is whether the urgency of the scientific question, are we alone, is sufficient to drive the investment needed to develop those capabilities on a timeline measured in decades rather than centuries. In 2024, Europa Clipper is in flight. In 2030, it will begin its Europa flybys. The answers it returns will shape everything that follows. This is the moment we are in. Not the moment of discovery, that may be decades away, but the moment when the investigation begins in earnest. The moment when humanity commits to asking this specific question with this specific instrument at this specific place. Everything we have discussed tonight, the radiation, the distance, the cold, the instability, the biological risk, the energy problem, the engineering complexity, all of it is the context for why this moment matters. We are going to Europa not despite the danger, but with full knowledge of it, because the question on the other side of that danger is worth it. Let us now talk about what an affirmative answer would actually mean, what it would mean scientifically, philosophically, and practically if Europa Clipper or a future mission found unambiguous evidence of life in Europa's ocean. The immediate scientific consequence, the theory of abiogenesis, the origin of life from non-living chemistry,
would be confirmed as a general process rather than an Earth-specific accident. Two independent origins of life in one solar system implies that wherever the conditions exist, life will emerge. With hundreds of billions of stars in our galaxy and probably trillions of planets, many with subsurface oceans maintained by tidal heating or radioactive decay, the implication is that life in the galaxy is not rare, it is probably common. The Drake equation, the framework for estimating the number of communicating civilizations in the galaxy, contains a term for the fraction of planets where life emerges. This term is currently the largest uncertainty in the calculation. A Europa detection would effectively set this term to 1. Wherever conditions permit, life happens. The consequences for estimates of the prevalence of life and intelligence in the universe would be profound.
The philosophical consequence, the question of whether we are alone, would be answered, definitively, in the negative. We would know that life is not a cosmic accident confined to one pale blue dot. We would know that the universe is, in some fundamental sense, alive, not just here, but elsewhere, independently, arising from the same chemistry under the same physical laws. This knowledge would be irreversible. Once known, it cannot be unknown. It would enter every subsequent human conversation about our place in the universe. Every religion, every philosophy, every conception of humanity's uniqueness would have to incorporate the fact that life arose independently in our own solar system, in an ocean most humans have never heard of, under a shell of ice orbiting the largest planet in the solar system. The practical consequence, it would redirect the search for life throughout the galaxy. Every ice-covered ocean world around every star would become a candidate. The habitable zone, currently defined as the distance from a star where liquid surface water can exist, would expand enormously to include any body with sufficient internal heating, regardless of distance from its star. The number of potentially habitable worlds in the galaxy would increase by orders of magnitude, and it would immediately raise the question of whether Europa's life shares a common origin with Earth life, delivered by meteorite exchange between the young solar system's rocky and icy bodies, or represents a genuinely independent second origin. This question alone would drive a century of scientific investigation. A negative answer would be equally significant in its own way. If Europa's ocean, chemically rich, thermally active, physically stable for billions of years, contains no life, this tells us that the barrier to life's emergence is very high. That something specific about Earth's conditions, perhaps its surface ocean and atmosphere, perhaps its moon and the tidal rhythms it creates, perhaps something we have not yet identified, is necessary in ways that the subsurface ocean environment does not provide. Both answers matter, both would change everything, and both are accessible to investigation. Not in this decade, not in one mission, but through the chain of missions that begins with Clipper, now in flight, continues with landers and penetrators in the 2040s and 2050s, and ultimately may include a vehicle that reaches the ocean itself. This is where the story of Europa's danger and Europa's significance converges. The danger is real. Every number we have discussed is real. 540 sieverts per day, years of transit, minus 160 degrees, 0.134 grams. The ice moving and cracking, the chemistry that corrodes, the biology that contaminates in both directions. And the significance is real. More liquid water than on all of Earth. Billions of years of stable conditions. Carbon in the ocean confirmed by Webb. Hydrothermal heat at the seafloor. All the prerequisites for life present and ongoing. The danger is the price of the question. The question is worth the price. That is Europa.
Let us talk about one more dimension of Europa that we have not yet fully explored, about what the Moon looks like from above, from the perspective of a spacecraft approaching it, because the visual character of Europa reveals something important about its nature that no amount of data tables can fully convey. The first close images of Europa came from Voyager 1 and Voyager 2 in 1979. At the time, planetary scientists expected another cratered, geologically dead moon, the default assumption for small icy bodies at that distance from the Sun. What they found was startling. Europa's surface was nearly free of impact craters. In a solar system that had been bombarded by impactors for billions of years, a body covered in craters is old. Its surface preserves a record of the bombardment because nothing has happened to erase it. A body with few craters has had its surface reshaped by geological processes that obliterate old craters as fast as new ones form. The Moon's surface is saturated with craters. It is geologically dead and has been accumulating them for billions of years. Mars has large craters in its ancient southern highlands and fewer in its younger volcanic north. Io has essentially no craters at all. Its volcanic eruptions resurface it continuously. Europa has very few craters. Its surface is geologically young by astronomical standards, resurfaced within the last tens to hundreds of millions of years by whatever processes are active in the ice shell.
This was the first indication, visible in the Voyager images, that something was happening inside Europa that was not happening inside dead, geologically inactive bodies. The Galileo mission provided far higher resolution images that revealed the surface in exquisite detail. The lineae, the network of dark, reddish-brown lines crossing the surface, turned out to be complex systems of ridges and troughs, often double ridges with a central trough between two raised parallel ridges, sometimes hundreds of kilometers long and extending across entire hemispheres. The leading model for these double ridges involves repeated cycles of cracking along a linear weakness in the ice, upwelling of material from below that fills the crack, refreezing, and then the next cycle of cracking. Over many cycles, the two flanking ridges build up from the repeatedly intruded material, while the central trough marks the active crack.
This process requires material from below, possibly ocean water or warm ice, to periodically reach or approach the surface along these linear features. If true, it means the lineae are windows of a sort into the subsurface, places where the chemical exchange between the ocean and the surface that Webb's CO2 detection suggests is occurring in a concentrated, linear fashion. The chaotic terrain regions, where the surface has been broken into irregular fragments that have shifted and rotated relative to each other, like an ice flow on a terrestrial river during spring breakup, represent the most dramatic evidence for surface-ocean interaction. In chaos regions, the ice has apparently lost coherence, broken into pieces and refrozen in new configurations. Some models propose that in these regions the ice thinned locally to the point where the ocean was nearly at the surface, or possibly briefly at the surface, before refreezing. If the chaos regions formed through partial melting from below, they represent places where the ocean was, geologically recently, only a few hundred meters from the surface, rather than kilometers. Whether such events are still occurring is unknown. The overall visual impression of Europa from close range is of a world that is alive in a geological sense, actively rearranging its surface, exchanging material between interior and exterior, maintaining a dynamic relationship between its ice shell and the ocean beneath. Not a static frozen ball, but a geologically engaged body, responding to the gravitational forcing of Jupiter and its sibling moons. This visual aliveness is why Europa looks the way it does. smooth, relatively uncratered, covered in a complex network of cracks and ridges that speak of ongoing activity, and why it is taken so seriously as a potentially biologically alive world as well. The geological aliveness and the potential biological aliveness are related. Both require the internal heat that tidal forcing provides. Both require the chemical exchange between ocean and surface. The same processes that make the surface look the way it does in images also create the conditions that could sustain life in the ocean below. Let us now talk about one aspect of Europa's situation that rarely appears in public discussion, but which any honest treatment must include, about what our ignorance actually amounts to specifically. We have confirmed that Europa has a subsurface ocean. We have confirmed from Webb that the ocean contains carbon. We have evidence from surface salt deposits that ocean material reaches the surface. We have evidence from magnetic measurements of the ocean's depth and salinity within ranges. We have theoretical models of hydrothermal activity at the seafloor. We have not measured the temperature of the ocean. We have not measured the pH. We have not measured the concentration of dissolved oxygen or other oxidants. We have not measured the distribution of hydrothermal vents or confirmed that any exist at the scale necessary to support ecosystems. We have not measured the total organic carbon content of the ocean. We have not confirmed the presence of phosphorus or nitrogen in forms useful to biochemistry. We have not measured the ocean's circulation patterns. We have not measured the rate of exchange between the surface ice and the ocean. We know enough to say the conditions are potentially habitable. We do not know enough to say they are certainly habitable, in the sense of having all the prerequisites in the right forms and concentrations. The difference between potentially habitable and certainly habitable is enormous, and is exactly what the next generation of missions must resolve. This distinction matters for calibrating expectations. The discovery of an ocean with carbon does not mean the discovery of life is imminent. It means the investigation is now warranted and pointed in the right direction. The path from potentially habitable to inhabited involves multiple steps, each requiring better data than we currently have. Europa Clipper will move us from potentially habitable toward characteristically habitable by measuring the ocean's magnetic signature with precision that constrains its salinity and depth, by mapping the ice thickness to identify thin spots and active exchange regions, by analyzing plumes, if they exist, to characterize the ocean's chemistry from above. A future lander would move us from characteristically habitable toward measurably habitable at the surface, by directly analyzing ice that has been in recent contact with the ocean and measuring the specific chemical signature of whatever chemistry is occurring. A future ocean probe would move us from measurably habitable to inhabited or sterile, by directly sampling the ocean and looking for the chemical or biological signatures of life. Each step requires the previous step's data to be motivated and designed effectively. Each step is its own major engineering and scientific challenge, and the final step, the ocean probe, is a challenge that dwarfs everything that has come before in terms of both technical difficulty and philosophical weight. This is the honest scientific picture of where we are and how far we have to go. Not pessimistic, the direction is clear and the tools are coming, but realistic about the magnitude of the journey from where we are to where we need to be to actually answer the question. Let us now talk about something that connects the technical picture we have been building to the human story underneath it, about the specific people who have dedicated their professional lives to understanding Europa and what drives them. Planetary science is a field with unusual motivational dynamics. The objects being studied are unreachable by the scientists studying them. A geologist can visit the formations they study. A biologist can observe the organisms they work with. A planetary scientist working on Europa is separated from their object of study by hundreds of millions of kilometers, years of transit, and a radiation environment that kills in 20 minutes. They work with data from instruments they designed years or decades earlier, launched on missions they spent careers advocating for, which returned data after voyages lasting years. The time from initial concept to scientific result in this field spans entire careers. Many scientists who contributed to the Galileo mission's Europa discoveries began that work before some of their graduate students were born. The scientists on the Europa Clipper team have similarly invested decades. The principal investigators of Clipper's instruments have spent much of their professional lives on instrument design, calibration, testing, and the years-long wait from launch to arrival. When Clipper begins its Europa flybys in 2030, it will be delivering scientific return on investments of time and intellectual effort that in some cases go back to the 1990s. This temporal scale, the multi-generational character of outer solar system exploration, means the people doing the science cannot expect to see the complete arc of the story they are contributing to. They are writing chapters of a book they will not finish. They are building a ladder they will not climb to the top. And they do it anyway.
This is not unique to planetary science. It is true of fundamental physics, of genomics, of many fields where the deepest questions take generations to answer. But it is particularly vivid in Europa science because the question is so specific, so answerable in principle, and so far from being answered in practice. The question, is there life in Europa's ocean, is a yes or no question that nature has a definite answer to. Unlike many scientific questions that resolve into nuanced probabilistic statements, this one has an answer that is either yes or no. Either there is life there or there is not. That definiteness, the knowledge that the question has a specific answer that could in principle be obtained, is part of what drives the field. Scientists working on Europa are not chasing an infinitely receding horizon. They are working toward a specific, answerable question whose answer exists right now in an ocean several 100 million kilometers away. Whether they personally live to see the answer is a different question. Many will not. But the work they do now shortens the distance between humanity and that answer. It is work that has meaning beyond any individual career or lifetime. This is, in some ways, the deepest thing that can be said about Europa science, and about why the danger of the environment there, which we have spent so much of this discussion characterizing, does not diminish the motivation, but in some sense intensifies it. The harder something is to reach, the more significant the reaching becomes. The more dangerous the environment, the more the question it poses demands to be asked. Europa is dangerous, more dangerous than Mars, more dangerous than anywhere else we have seriously contemplated sending human beings. And it poses one of the most important questions in the history of science. These two facts are not in conflict. They are the same fact, seen from different angles. The danger is the measure of the distance to the answer, and the answer is worth the distance. Let us now talk about one last concrete thing before we bring this long discussion to its close, about what you can actually observe of the Europa system with accessible instruments, and what that observation means in the context of everything we have discussed. Jupiter is currently visible in the night sky as one of the brightest objects, a steady, slightly yellowish point that does not twinkle like the surrounding stars. In binoculars, ordinary 10 by 50 binoculars of the kind available for modest cost, Jupiter appears as a small disk accompanied by up to 4 points of light arranged in a rough line through the planet's equator. These are the Galilean moons: Io, Europa, Ganymede, Callisto, the 4 largest moons of Jupiter,
the four that Galileo himself observed in January 1610, and whose motion around Jupiter provided him the first evidence of a celestial body orbiting something other than Earth. Europa is typically one of the two innermost points visible. It orbits closest to Jupiter among the four easily visible moons, and is rarely far from the planet in the view. Its orbital period of 3.5 days means it moves noticeably from night to night, tracing an arc around Jupiter that completes in under a week. To the naked eye, it is indistinguishable from a star. In binoculars, it is a point of light. In a modest amateur telescope, 80 to 100 mm aperture at 100 times magnification, it is still a point of light. No surface detail is visible from Earth with any amateur instrument. And yet that point of light contains more liquid water than all of Earth's oceans combined. It is being stretched and squeezed by Jupiter's gravity right now. Its ice is cracking. Its ocean is in contact with a rocky seafloor. Its surface is receiving 540 sieverts of radiation per day. And it may be alive. That point of light, indistinguishable from the surrounding stars to the unaided eye, may be the most significant place in the solar system from the perspective of the question that has occupied human curiosity since humanity was capable of curiosity. This is what Europa is, a point of light that might change everything. The danger of going there is real. The significance of what might be found there is commensurate with that danger. That is the honest account of Europa's place in the story of human exploration. Let us talk about what the specific orbital mechanics of Europa mean for mission design, because this is a concrete engineering reality that shapes everything about how we can approach this moon, and understanding it clarifies why even robotic exploration is so difficult. Europa orbits Jupiter at a distance of about 671,000 kilometers, with an orbital period of 3.551 days. This places it deep within Jupiter's radiation belts, not at the inner edge, not at the outer edge, but squarely in one of the most intense regions of the Jovian magnetosphere. The radiation intensity varies with distance from Jupiter in a complex way determined by the structure of the magnetic field and the distribution of trapped particles. The innermost Galilean moon, Io, is actually somewhat shielded from the worst radiation because it orbits within the region where the radiation belts are still building up their full intensity. Europa, slightly further out, sits near the peak of the electron flux distribution, precisely where the radiation is most intense. Ganymede, further still, receives less radiation, both because of distance and because of its own intrinsic magnetic field deflecting some of the incoming particles. Callisto, furthest of the four major moons, is outside the main radiation belts entirely and receives a comparatively modest radiation dose. This orbital placement of Europa is not random. It is determined by the same gravitational dynamics that drive the tidal heating of the Moon. Europa is in a Laplace resonance with Io and Ganymede. For every orbit Ganymede completes, Europa completes exactly 2 orbits, and Io completes exactly 4. This 1 to 2 to 4 resonance is gravitationally locked. It self-perpetuates because any deviation from exact resonance is corrected by the gravitational interactions between the moons. This resonance forces Europa's orbit to remain slightly elliptical rather than perfectly circular. A perfectly circular orbit would experience constant tidal forces, and the Moon would be tidally locked with no ongoing deformation. The elliptical orbit means the distance to Jupiter, and therefore the tidal force, varies slightly over each orbit. This variation in tidal force is what continuously flexes and heats Europa's interior. It is what maintains the liquid ocean. It is what drives the geological activity we see at the surface. The Laplace resonance sustains Europa's ocean. It also places Europa at the radiation dose rate that makes its surface lethal. These two facts are connected at their root. The same orbital configuration that provides the energy source for the ocean produces the radiation environment that kills. You cannot have one without the other, without fundamentally changing Europa's orbital position in the Jupiter system. And changing Europa's orbital position would remove it from the resonance, eliminate the tidal heating, and eventually freeze the ocean. Europa is what it is because of where it is. Its habitability and its danger are both consequences of the same orbital mechanics. This is worth sitting with as a physical fact. The ocean that might be alive is sustained by the same gravitational system that makes the surface lethal to approach. The question of life in that ocean can only be asked from the surface of a moon that kills anything that stands on it unprotected. The universe does not simplify things for the convenience of those asking questions. Let us now talk about what the Europa Clipper spacecraft actually looks like and how it is designed to survive in the environment we have been describing, because the engineering of the spacecraft itself is a physical embodiment of the challenges. Europa Clipper is a large spacecraft. With its solar panels deployed, it spans about 30 meters, comparable in size to a basketball court. This large size is necessary primarily because of the enormous solar panels required to generate sufficient power at Jupiter's distance from the Sun. As we discussed, solar flux at Jupiter is only about 3.7% of what it is at Earth. Generating the roughly 600 watts of power the spacecraft needs at Europa's distance requires very large solar arrays. The spacecraft's electronics, its computers, science instruments, communication systems, are housed in a heavily shielded vault. This vault is constructed primarily from aluminium and zinc, materials chosen for their radiation shielding properties. The vault attenuates the radiation environment inside to a level the electronics can survive over the mission's lifetime. Despite this shielding, the electronics are still exposed to more radiation than spacecraft operating in gentler environments. This is why Clipper uses radiation-hardened components, older generation chips with larger transistor sizes that are less susceptible to radiation-induced damage. Modern consumer electronics use transistors measured in nanometers. These are extraordinarily sensitive to radiation. The chips in Europa Clipper are deliberately less advanced in transistor size to be more robust. The mission is designed around the flyby strategy, specifically to limit radiation exposure. Clipper spends most of its time in the radiation environment further from Jupiter, completing its elliptical orbit that takes it far from the Moon between flybys, and dives to Europa only for close approaches lasting a few hours at a time. During each flyby, the instruments gather data intensively, and then the spacecraft retreats to safer distances while the data is processed and transmitted. The total radiation dose accumulated by Clipper over its planned mission, roughly 50 Europa flybys over 4 years, is designed to remain within the tolerance of the radiation-hardened components. There is margin built in, but the margin is not large. The spacecraft will be operating at the edge of what the electronics can tolerate by the mission's end. This is a spacecraft designed to exist at the limit of what is survivable in an environment designed to kill electronics just as it kills biology. The engineering of Europa Clipper is the current answer to the question of how to work in a place that does not want to be worked in. Let us now talk about something that has emerged from thinking about Europa in the context of astrobiology more broadly, about the concept of the ocean world and what it implies for our search strategy for life beyond Earth. For much of the 20th century, the search for extraterrestrial life was implicitly guided by what we might call the surface assumption.
The idea that life, to be detectable and to be in a state complex enough to be interesting, would exist on the surface of a planet. This assumption was shaped by our only example of life, Earth's biosphere, which is predominantly a surface phenomenon. Even Earth's deep life, the subsurface microorganisms living in rock pores kilometers down, was not known until the 1980s and 1990s. The search for life in the solar system for most of the 20th century focused on Mars, a surface world, and on Venus before we understood its surface conditions. The search for extraterrestrial intelligence focused on radio signals from civilizations that, by implication, were technological societies on planetary surfaces. The discovery of Europa's ocean, followed by the confirmation of Enceladus's ocean and active plumes, followed by growing evidence for oceans on Ganymede, Callisto, Titan, and possibly Pluto and several smaller bodies, has revealed that the solar system contains far more liquid water in subsurface oceans than it does on any surface. Earth's surface oceans are enormous by the standards of any terrestrial body, but Europa's ocean alone exceeds Earth's total ocean volume. The combined subsurface oceans of the icy moons of Jupiter and Saturn may represent a reservoir of liquid water an order of magnitude larger than Earth's surface oceans. Most of the liquid water in the solar system is not on the surface of any planet. It is under ice. This realization, if generalized to other star systems, completely transforms the concept of the galactic habitable zone. The traditional habitable zone is defined as the range of distances from a star where surface liquid water can exist, roughly 0.95 to 1.7 astronomical units from a Sun-like star. This zone is narrow. Many planets fall outside it. The fraction of star systems with planets in the traditional habitable zone is limited. But if subsurface oceans, maintained by tidal heating or radioactive decay, can support life, the relevant parameter is not distance from the star, but the presence of a mechanism to maintain liquid water regardless of surface temperature. Tidal heating requires the right kind of orbital resonance, not universal, but common around gas giants with multiple large moons. Radioactive decay heating from long-lived radioactive isotopes is nearly universal in any body large enough to retain its internal heat. The number of potential subsurface ocean worlds in the galaxy, moons of gas giants and ice giants, dwarf planets at large distances from their stars, potentially even free-floating planetary bodies with no star at all, could be enormous. We have no census of these worlds. We have barely begun to characterize the ones in our own solar system. Europa is the most accessible test case for this broader question. What we learn at Europa about whether subsurface tidal ocean worlds can host life directly informs our assessment of life's prevalence throughout the galaxy. It is not merely a question about one moon of Jupiter. It is a question about whether the most common type of potentially habitable environment in the galaxy, the subsurface ocean world, is actually inhabited. Let us now talk about the specific way that Europa fits into the most fundamental question in science, about whether life is a feature of the universe or an accident of Earth. This question, sometimes framed as whether we are alone, is deceptively simple in phrasing and almost incomprehensibly profound in its implications. It has been asked in various forms since antiquity. It underlies astrobiology, SETI, the study of extremophiles, and the entire enterprise of Mars exploration. It motivates the search for biosignatures in exoplanet atmospheres. It is the question that Europa most directly addresses within our own solar system. The current state of knowledge gives us no answer. We have one data point, Earth, where life arose under conditions that we can characterize in some detail. We cannot tell from one data point whether life's origin is a near certain consequence of the right chemistry under the right physical conditions, or an astronomically improbable event that happened by chance and may not have happened anywhere else. Statistics require multiple data points. A second origin of life, anywhere in the solar system, in any form, would transform this from a one data point problem into a two data point problem. 2 data points is not a large sample, but it is the difference between life arose once under conditions we can study and life arose independently in 2 different environments under conditions we can compare. The comparison is what matters scientifically. If life exists in Europa's ocean, we can study it. We can compare its biochemistry to Earth's. Does it use the same genetic code, the same amino acids, the same chiral handedness? The answers to these questions would tell us whether Europan and Earth life share a common ancestor, delivered by meteorite exchange between the young solar system's bodies, or whether they represent genuinely independent origins. 2 independent origins of life in one solar system would be a profound finding. It would indicate that life is not a cosmic accident, but a robust physical process that occurs wherever the conditions allow. Combined with the enormous number of potential habitable environments in the galaxy, surface habitable zone planets, subsurface ocean moons, diverse other environments, it would imply a galaxy teeming with life. A single shared origin, if Europan and Earth life prove to be related, would be less immediately dramatic, but equally interesting. It would tell us that life can spread between worlds within a solar system through meteoritic exchange, that planetary biospheres are not necessarily isolated from each other, and that the solar system may have been a single biological system early in its history. A sterile Europa, no life despite apparently suitable conditions, would be equally informative in the opposite direction. It would suggest that the barrier between chemistry and biology is high enough that even 4 billion years of apparently suitable conditions does not guarantee life's emergence. It would make the origin of life on Earth look more like a rare accident and make the galaxy look potentially much emptier. All 3 outcomes change our understanding of our place in the universe. None is the wrong answer scientifically. All are worth knowing. And all are potentially knowable, not soon, not easily, but within the horizon of what serious long-term scientific effort can achieve. Europa is where that effort is most directly pointed within our solar system. Let us now talk about what we hope the next decade will reveal, not just from Europa Clipper, but from the broader maturation of our understanding of ocean worlds. By 2035, assuming Europa Clipper operates as designed, we should know the thickness of Europa's ice shell across a significant fraction of its surface, with enough resolution to identify regions where the shell is thin enough to potentially permit chemical exchange with the ocean on geological timescales. Whether Europa has active plumes, whether material from the ocean is being actively vented to space in a way that makes it accessible for chemical sampling without surface contact. The salinity and approximate depth of the ocean from magnetic measurements, which constrain the ocean's chemistry in ways that inform habitability assessments. The detailed surface geology of Europa at resolutions approaching 1 meter per pixel in selected areas, identifying specific geological features that most directly sample ocean-derived material. The chemical inventory of Europa's surface in detail from multiple spectroscopic instruments, extending and confirming the Webb CO2 detection with far higher spatial resolution and broader spectral coverage. This knowledge will not answer whether life exists in Europa's ocean,
but it will tell us whether the ocean's chemistry is compatible with life in specific, quantitative ways. Not just there is carbon, but there is carbon and nitrogen and phosphorus at concentrations that support Earth-like biochemistry. Or, conversely, the ocean chemistry is unusual in ways that might challenge biochemistry as we understand it. It will also tell us where the next mission should go. Which regions of the surface have the most recently exchanged material with the ocean? Where the ice is thin enough to make a future drill mission feasible with realistic technology. Where the plumes offer a shortcut, a way to sample the ocean without drilling at all. By 2035, if Clipper performs as hoped, we will not have answered the question, but we will be in a far better position to know how to answer it. What specific measurements are needed? What specific locations on the surface are most scientifically valuable? What type of mission should follow? This is how science at this scale actually progresses. Not dramatic leaps, but carefully guided steps, each one informed by the previous, each one reducing the uncertainty and sharpening the question until the answer becomes accessible. Europa is the most important object in the solar system for the question of whether life is a universal feature of the cosmos or a terrestrial accident, and it is one of the most dangerous places any human might ever go. Those two facts live together. The danger does not diminish the importance. The importance does not diminish the danger. They coexist as the fundamental character of this particular place, a moon of Jupiter, 35 times the distance from the Sun as Earth, covered in ice, bathed in lethal radiation, harbouring an ocean larger than all of Earth's combined. A point of light in a telescope, a potential answer to one of the oldest questions human minds have asked. Let us talk about something we have touched on but not examined in full depth, about what the specific detection of life in Europa's ocean would actually look like in practice, and why this is harder than it might initially seem, even if life is present. The challenge of detecting life is not simply a matter of going to Europa and looking. Life, especially microbial life, is not always obvious even on Earth in environments we can examine directly. The deep subsurface biosphere of Earth, microorganisms living in rock pores kilometers underground, was not discovered until the 1980s and 1990s, and its full extent is still being mapped. These microorganisms are present at very low concentrations, sometimes only hundreds of cells per milliliter of pore water, and metabolize at extraordinarily slow rates, dividing perhaps once per 1,000 years. If Europa's ocean harbours life, it might be of a similar character. Not the visible, dense mat of organisms that surrounds hydrothermal vents in Earth's deep oceans, though those would be exciting to find, but possibly sparse, slow metabolizing microorganisms distributed through the ocean at low concentrations, doing chemistry at rates so slow that the chemical signatures they produce are subtle relative to the background. Detecting such life requires sensitive instruments, clear biosignatures, and the ability to distinguish biological signals from abiotic chemistry. What would constitute a biosignature in Europa's ocean? The most direct evidence would be the presence of living cells, objects with cell membranes, genetic material, metabolic activity. A future microscope on a surface lander examining freshly sampled ice could potentially see cell-like structures if they were present in material that had recently exchanged with the ocean. Cell morphology, shape, size, internal structure, can distinguish biological from mineral particles in favourable cases. But cell detection requires physical samples of ocean material, high-resolution microscopy, and careful interpretation. False positives, mineral particles that superficially resemble biological cells, are a genuine concern. Chemical biosignatures are potentially more accessible. Life on Earth produces specific chemical signatures that distinguish it from abiotic chemistry. The relative abundances of different amino acids In living systems, the 20 standard amino acids are heavily favoured, while abiotic chemistry produces a much broader range, can indicate biological activity. The chirality of organic molecules. Life on Earth uses exclusively left-handed amino acids and right-handed sugars, while abiotic synthesis produces equal mixtures, is a particularly powerful biosignature. A mass spectrometer capable of distinguishing amino acid chirality, measuring the relative abundances of different amino acid types, and detecting other biomarkers, lipids, nucleobases, specific isotopic ratios, in a plume sample or a surface ice sample, could potentially identify life without direct cell detection. MASSPEX, the mass spectrometer on Europa Clipper, is highly sensitive and capable of detecting a broad range of organic compounds. If Clipper flies through a plume that samples ocean material, MASSPEX could detect organic compounds, including amino acids, if they are present in sufficient concentrations. But sensitivity has limits. A very sparse microbial community might not produce enough organic material in the plume to exceed MASSPEX's detection thresholds. Dilution between the ocean and the plume, the ocean material is mixed with ice during the eruption process, further reduces concentrations. This is why positive detection by Clipper of specific biosignatures would be extraordinary, but negative detection would not prove absence of life. It would constrain the possibilities. Life abundant enough to produce detectable plume signatures can be ruled out if plumes are found and no biosignatures detected. But a sparse or deeply distributed biosphere could remain undetected. This realistic picture of what detection involves is important context for evaluating what Clipper can and cannot tell us. It is not an instrument that can look at Europa and say yes or no to life. It is an instrument that can characterize the chemical environment, search for specific signatures if plumes provide samples, and guide future missions to the best locations for more definitive investigation. The definitive investigation, if it ever comes, involves physical samples of ocean water analyzed with instruments capable of detecting and characterizing microbial life at low concentrations. That requires penetrating the ice. That requires an ocean probe. That is a mission of the 2060s at the earliest, and more likely the 2070s or 2080s. The path is long. The science is proceeding step by step. Each step is motivated by the question and informed by the previous step's data. Let us now talk about a specific aspect of Europa's potential biology that is rarely discussed, about what evolution might produce in an isolated subsurface ocean over 4 billion years. On Earth, life originated approximately 3.5 to 4 billion years ago from relatively simple chemistry and has been evolving continuously since. The trajectory of that evolution, from simple prokaryotic cells to complex eukaryotic cells, from single-celled organisms to multicellular organisms, from simple organisms to organisms with nervous systems and eventually intelligence, is familiar. But Earth's biosphere has had enormous advantages that a Europa ocean biosphere might lack. Sunlight provides abundant, reliable, concentrated energy that drives highly productive photosynthetic ecosystems. These photosynthetic ecosystems produce vast quantities of oxygen that transformed Earth's atmosphere and opened up aerobic metabolism, a far more energetically efficient way of extracting energy from organic molecules than anaerobic alternatives. The diversity of surface environments, mountains, rivers, oceans, deserts, polar regions, provides enormous ecological diversity that drives evolutionary innovation. Europa's ocean has none of these advantages. It is dark. Its energy supply is chemical, from hydrothermal vents, and limited to the thermodynamic potential of those vents. Its environment is relatively homogeneous, cold, dark, high pressure, with gradients primarily at hydrothermal vent sites. It has been isolated from the cosmic input of energy that drives Earth's richest ecosystems. What might 4 billion years of evolution produce in such an environment? The most likely outcome, if life exists at all, is an ecosystem of simple microorganisms, perhaps diverse in metabolic strategies, but lacking the energetic surplus that drove the complexification of Earth's biosphere.
Something analogous to Earth's deep subsurface biosphere, diverse, persistent, ecologically functional at the microbial level, but not providing the energetic foundation for complex multicellular organisms. This is the responsible expectation, not aquatic creatures analogous to fish or mammals, not anything with a central nervous system or behavioral complexity analogous to what we see in Earth's marine vertebrates. The energy budget of a Europa ocean driven by hydrothermal chemistry is simply too limited to support the productive base that complex multicellular life requires.
The finding most likely would be, if life is there, something that looks under a microscope like a diverse community of microorganisms with varied morphologies and metabolic strategies, chemically distinct from Earth life in specific ways that reflect independent origin, perhaps using a different genetic code or different amino acid set or different membrane chemistry, but recognizable as life in its fundamental organization. That would be enough. That would be revolutionary. That single finding, simple microbial life in Europa's ocean, distinct from Earth life, would be the most significant scientific discovery in human history, full stop. The absence of complex multicellular life would not diminish it. The simplicity of the organisms would not diminish it. The finding of any life, independent of Earth's, would answer the fundamental question in the most definitive possible way. We are alone in the universe, or we are not. Europa can tell us which. Let us now talk about the specific question of what comes after a positive detection, about the scientific and practical implications of finding life in Europa's ocean, and what the response would be. The immediate scientific response would be intensive characterization. Where is the life concentrated? What metabolic strategies does it use? What is its genetic code or its equivalent information storage mechanism? What is its biochemical relationship to Earth life, shared ancestor or independent origin? These questions would drive multiple follow-up missions. The first ocean probe would need to be followed by vehicles capable of longer-term sampling across different regions of the ocean, different depths, different distances from hydrothermal vents. Mapping the biological diversity of an ocean the size of Europa's, even at the microbial level, would be a decades-long project. The planetary protection implications would be immediate and severe. If life exists in Europa's ocean, the case for protecting it from Earth contamination becomes overwhelming. Any human mission to Europa in the context of confirmed extant life would need to maintain absolute biological isolation from the ocean, a requirement that makes the already extreme challenges of human presence on Europa even more demanding. It would also raise an entirely new question. What rights or moral status, if any, does extraterrestrial microbial life have? This question would move from philosophical speculation to practical urgency. If we find living microorganisms in Europa's ocean, any activity that risks introducing Earth biology or destroying native organisms becomes a moral question, with no established framework for answering it. These are genuinely difficult questions that human institutions, scientific, legal, philosophical, religious, are not currently prepared to answer with any consensus. The discovery would force a global conversation about what obligations humanity has toward other forms of life, regardless of how simple those forms are. The political implications would be substantial. Who owns the data from a positive detection? Who decides what follow-up missions are permitted? Who speaks for humanity in establishing planetary protection protocols for a confirmed living ecosystem? These are governance questions that currently have no clear answer and would need to be addressed urgently in the context of a finding that the entire world would immediately be aware of. The cultural and psychological implications are harder to predict precisely, but easy to imagine in outline. The knowledge that we are not alone, that life exists independently of Earth in our own solar system, would reverberate through every human institution and every individual consciousness. The implications for religion, for philosophy of mind, for concepts of cosmic significance and human uniqueness, for every tradition that has interpreted human existence in terms of its relationship to the rest of the cosmos, all of these would be touched, and some of them fundamentally altered. This is not hyperbole. It is a straightforward accounting of what the discovery would mean. The discovery would also be the greatest single motivator for continued space exploration in human history. Every ocean world in the solar system would immediately become a priority for investigation. Every candidate habitable environment, subsurface oceans on the moons of Saturn, Uranus, Neptune, on dwarf planets in the Kuiper Belt, would receive urgent attention. The search for biosignatures in exoplanet atmospheres would be pursued with resources never previously available. The answer yes to the question of whether we are alone would transform the entire human project of exploring the cosmos.
Let us now talk about what the answer no would mean, because negative results in science are often undervalued but can be equally important. If Europa's ocean is sterile, if a future ocean probe finds water, minerals, chemistry, hydrothermal activity, all the apparent prerequisites for life, but no life, this is a finding of equal scientific significance. It would tell us that the prerequisites we have identified are not sufficient, that something else, something we do not currently understand, is necessary for the origin of life. This would redirect the study of abiogenesis, the origin of life from chemistry, toward finding what that missing factor is. It would tell us that life on Earth may be genuinely rare, that the specific history of early Earth, perhaps its surface liquid ocean exposed to sunlight, perhaps its relationship with the moon that drives tidal rhythms, perhaps some geochemical accident in the early ocean, perhaps the specific combination of all these factors produced something that does not happen automatically from water and chemistry and heat. This would be a humbling result. It would imply that in a galaxy with hundreds of billions of stars, life might be extraordinarily sparse, perhaps only on planets very similar to early Earth, in very specific configurations, under very specific conditions that we have not yet fully characterized. The Fermi paradox, why, if intelligent life is common, have we not detected it, would find a new partial resolution. If life itself is rare rather than intelligence alone being rare, the silence of the cosmos becomes easier to understand. A sterile Europa would not end the search for life beyond Earth. It would redirect it towards surface environments with sunlight, toward understanding what Mars might have held in its distant past, toward searching for Earth-like planets in other star systems with the persistence that a genuinely rare phenomenon demands. Both yes and no are worth knowing, and only one place in the solar system offers a chance at an answer within the timescale of human civilization as we currently imagine it. That place is Europa. Dangerous, brilliant, possibly alive, possibly sterile. certainly the most important scientific destination in the solar system for the question that matters most. Let us now talk about something that brings this discussion back to the immediate present, to what you can do right now, tonight, to connect to the story we have been telling. Europa Clipper is flying. Right now, as you read or listen to this, the spacecraft is in transit from Earth to Jupiter. It was launched on October 14th, 2024, aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center. It is following a trajectory that takes it past Mars for a gravity assist in March 2025, then past Earth again for a second gravity assist in December 2026, before the long journey to Jupiter arriving in April 2030. You can track Europa Clipper's position in real time on NASA's Eyes on the Solar System, a publicly available visualization tool that shows the current position of all active NASA spacecraft. The spacecraft is currently somewhere between Earth and Mars, moving at tens of thousands of kilometers per hour through the inner solar system. This is not an abstraction. The mission is real, in progress, happening now. The spacecraft that will tell us more about Europa than we have ever known is in flight. In 2030, 6 years from this moment, it will arrive at Jupiter. It will begin its survey of Europa. The data it returns will reshape what we know about that small white point visible in binoculars next to Jupiter. In the years from 2030 to 2034, the question of whether Europa's ocean is chemically suitable for life, whether it contains the specific ingredients in the specific forms that biology requires, will become dramatically better constrained. Not answered, but better constrained than it has ever been. This is the immediate horizon, not science fiction, not indefinite future. 6 years to arrival, 4 years of flybys. A decade from now, we will know what we do not know today. You can look at Jupiter through binoculars or a small telescope and know that one of those 4 points of light arranged near the planet is the place toward which that spacecraft is headed. That one of those points is more water than all of Earth's oceans. That one of those points has radiation that kills in 20 minutes. That one of those points may be alive. The universe extends from there to the limits of what we can see. Most of it is empty. Much of it is inhospitable. Some small fraction of it, a fraction we do not yet know the size of, may be inhabited. Europa is where we are currently looking for the answer. The danger of getting there is real. The significance of what might be found is commensurate. The work is underway. The spacecraft is in flight. And the question, simple, specific, answerable, perhaps the most important question humanity has ever formulated, waits in that ocean beneath the ice. Go outside tonight. Find Jupiter. It is one of the brightest points in the sky, steady, slightly yellowish, not twinkling like the stars around it. If you have binoculars, point them at Jupiter. At any reasonable magnification, you will see up to 4 faint points arranged in a line through the planet. These are the Galilean moons. The same 4 points Galileo observed in January 1610 with a telescope he built himself 4 centuries ago, and whose movement around Jupiter changed everything we thought we knew about the cosmos. One of those points is Europa. Look at it. That point of light, indistinguishable from a faint star, requiring binoculars to see at all, contains more liquid water than all of Earth's oceans combined. Its subsurface ocean is confirmed. Its carbon chemistry has been detected by the James Webb Space Telescope. Its ice is cracking and moving right now under the tidal pressure of Jupiter's gravity. Its rocky sea floor may be in contact with hydrothermal systems, providing chemical energy to anything living above them. And right now, tonight, while you are outside looking at it,
It is receiving 540 sieverts of radiation per day at its surface. A lethal dose for a human being is about 8 sieverts. An unprotected person standing on Europa's surface would be dead in 20 minutes. This is the specific character of Europa. Not merely dangerous, not just more difficult than Mars, though it is both of those things by every measurable parameter. Qualitatively different. A place where the conditions that might sustain life in the ocean below are produced by the same system that makes the surface immediately lethal to anyone who tries to reach it. Jupiter's gravity heats Europa's interior. That heating sustains the liquid ocean. That ocean may contain life. Jupiter's gravity also drives the orbital resonance that places Europa inside the most intense radiation belts in the solar system. Those radiation belts kill. The thing that makes Europa possibly alive makes its surface kill. This is not a problem that engineering eventually solves by making everything easier. It is a fundamental physical reality about this particular place. The energy that runs the ocean and the radiation that kills the visitor come from the same source. And yet, there is a spacecraft in flight right now heading toward Europa. Europa Clipper, launched October 2024, currently somewhere between the orbits of Earth and Mars, moving at tens of thousands of kilometers per hour through the inner solar system. In 2030, it arrives at Jupiter. It will perform roughly 50 close flybys of Europa over 4 years, diving into the radiation environment briefly with each pass, its electronics protected by a shielded vault, its instruments pointed at the surface, and the space above it looking for plumes, measuring the ice thickness, reading the chemistry. It will not answer the question. It will not tell us definitively whether Europa's ocean is inhabited, but it will tell us whether the ocean's chemistry is compatible with life in specific, quantitative ways, whether the ice is thin enough in certain regions to permit future drilling, whether plumes carry material from the ocean into space where a future spacecraft can sample it directly, whether the ocean's salinity and depth match what biology requires. And whatever Clipper finds will shape the mission that comes after it, which will shape the mission after that. Each step narrowing the uncertainty, sharpening the question, bringing the answer closer. Eventually, not in this decade, not in the next, but within the horizon of serious long-term scientific effort, a probe will reach that ocean. It will sample the water. It will look for the signatures of life. And it will find something, either life or the absence of life. Either answer changes everything. If life is there, if microorganisms are swimming or clinging to hydrothermal vents in that dark, cold, pressurized ocean, then we are not alone. Life arose independently in our solar system at least twice. The barrier to life's origin is low. The galaxy, with its hundreds of billions of stars and probable trillions of ocean worlds, is almost certainly teeming with life. We are one voice in a vast biological universe we have barely begun to understand. If the ocean is sterile, if after 4 billion years of liquid water and chemical energy and all the apparent prerequisites, nothing lives there, then the origin of life is rarer than we hoped. Earth may be genuinely exceptional. The cosmos may be mostly quiet. The silence of the universe that we have never fully explained may find a partial answer in the sterile ocean of a frozen moon. Both answers matter. Both deserve to be known. Europa is where we are looking. That small point of light next to Jupiter bright enough to see in binoculars, too faint for the naked eye. That specific, particular object in our solar system is the place in the cosmos where we have the best chance of answering the oldest question human minds have asked. Are we alone? The spacecraft is in flight. The ocean is waiting. The question has an answer. We are going to find it.